Welcome everyone to this version of the Distinguished Lecture Series here at the Max Planck Institute for the Science of Light. We also welcome those joining us online. As you know, the Distinguished Lecture Series is our main venue at the Max Planck Institute for the Science of Light, bringing you the international thought leaders in this domain. And in the following hour, we will listen to our visitor of today, whom I'm now going to introduce. Professor Isabelle Staude is professor at the University in Jena for nanophotonics. Briefly, I want to say something about her CV. She studied physics in Konstanz. She then went to the Karlsruhe Institute of Technology, where in 2011 she finished her Ph.D. in the group of Wegener. Afterwards, she went to the Australian National University, so to the other side of the globe. And in 2015, she finally returned to Germany to take up an independent group leader position in Jena, where she then also had an Emmy-Noether junior group. And in 2020, she was appointed professor for photonic nanomaterials in Jena. Her very well-known work is about metasurfaces, metamaterials, and 2D materials. Her work is extremely well cited. We will today hear something about one part of what she does, namely metasurfaces. She also received numerous awards, such as in 2017, she received the Hertha Sponer Prize of the German Physical Society, and she was elected member of the Junge Akademie of the Leopoldina National Academy of Sciences. And so please join me in welcoming again Isabelle Staude. We are looking very much forward to your talk.
Yeah, thank you so much for the very kind introduction. It's really a pleasure and also honor to stand here today and talk to all of you. I already learned so many interesting things in the morning and look forward to some more program in the afternoon. So it's actually my second visit to the MPL, but the last one was before you moved in this beautiful new building. So there's been quite something happening here on your end. And let's see. I want to show you today something about, as already announced, about metasurfaces, namely active metasurfaces. This is what I will concentrate on. And so I will basically jump directly into the content. I now realize maybe I should have put a slide for Jena, but I think maybe you all know Jena. It's quite close, and there's already a lot of connections through the Max Planck School of Photonics, for instance. So I think we are well-known partners, and maybe Jena doesn't need any big introduction in this audience anymore. Yeah. So, but if you're interested, also in visiting us, please let me know. We are very happy to welcome you also in Jena. All right, so everything I'm going to show, of course, is a team effort as usual in science, and I tend to get a bit tight on time in the end, so I like to acknowledge my collaborators in the beginning. And so we have a lot. Ooh, okay, no. Wrong button. Okay. So of course we collaborate very actively within Jena, with the groups shown there. Then also you heard I did my postdoc in Australia, so there are still very strong links with the Australian National University. We actually also have joint funding for graduate school, educating Ph.D. students together on a larger scale. We collaborate with Sandia Labs, as you also do, so Igal is also a well-known scientist here, and KIT, Norfolk State, and also the MPL. So we have I will very briefly show this joint work with Masha. So let's see. Okay, so this will be the outline of my talk. As usual, there will be some motivation and introduction, and then I will really focus on the, let's say, 3 dimensions of active that we are currently interested on, which is on the one hand tunable metasurfaces, light-emitting metasurfaces, and nonlinear quantum metasurfaces. And there will be a very brief outlook in the end. All right, let's start with the starting point. And I'm sure most of you really know what a metasurface is, but let me put it in some, to get a starter here. So it's basically a sheet of nanoscale thickness, which is here oriented out of the plane of the projector. And then the idea is we come in with some known input light field, and this metasurface transforms that into an output light field with desired properties, such as spectrum, polarization, wavefront, and so on. How does it do it? Okay, the magic lies here in the structure. So the metasurface is a two-dimensional sub-wavelength arrangement of designed nanoscale building blocks. And then here's this very simple cartoon. Probably these concepts are quite well known, but just to recap a little bit. So if, for instance, the metasurface implements something like a linear phase gradient, then some incoming plane wave would be deflected by it. And of course, these phase gradients can now be engineered by these nanoparticles and their arrangements. Yeah, so basically metasurfaces are related also closely to other concepts in nanophotonics. Quite obviously, they are related to metamaterials. You can see them as the two-dimensional counterparts of metamaterials. For metamaterials, the notion was often more to say, like, we want to create artificial media with optical properties that are not available in nature. Yeah? And this is, of course, a beautiful and powerful concept. But there were a few both conceptual and also practical problems and limitations, which by moving to the 2D geometry sort of disappear a little bit or become much better. Like, for instance, fabrication, of course, is much easier in a 2D plane. Yeah? Then, metasurfaces are also related to optical nanoantennas. If you want, particularly for these active geometries, you can consider also metasurfaces like a two-dimensional arrangement of nanoantennas. Yeah? And finally, sorry, I'm pressing, but I shouldn't. Finally, one shouldn't forget photonic crystals. Yeah, so if looking at a photonic crystal slab, it can sometimes look a lot also like a metasurface, and it's also not always easy to completely distinguish the two, because you may also see diffractive modes in metasurfaces. Yeah, but if you want to really make the distinction, can say, like, for a metasurface, really, you don't need periodicity and you don't need necessarily in-plane confinement. Yeah, and I think these are two things that would be strictly required in a photonic crystal slab. All right, so really wavefront shaping metasurfaces are maybe, or the wavefront is really, the outstanding property where metasurfaces were really utilized a lot in the past decade, maybe now, yeah? And if you look a little bit why there has been this hype happening. So basically, I showed you this little cartoon of the beam deflection, but of course now by engineering really the in-plane design of this metasurface, you can basically impose any spatial variation of phase onto your input light field. So in principle, your metasurface can emulate any kind of optical component like a lens, a beam deflector, a holographic phase mask, and so on. Yeah, and it can do that really in a very flat geometry. It can be very lightweight, it can be integrable. Also, this notion of optical function, like being multifunctional and highly tailorable, is something that has played a big role here. And I just want to show a little bit from the literature some works that I liked. For instance, if you think of applications of such wavefront shaping metasurfaces, people have been looking at this artificial and virtual reality, at holography and color generation, also at information processes. For instance, this is an example of edge detection here. And also in the quantum optics realm, they will be used really for characterizing quantum states. So one question to ask is what is the physical mechanism of the metasurfaces that engineers locally the phase? And there are actually various versions how this can be done. So maybe the three main ones would be to have a propagation phase. So some metasurfaces use sort of like upright standing little waveguides, and then by changing the cross-section of this waveguide, you can tailor the group delay in there, and thereby also the local phase that the input light field will pick up. Then there is the geometric phase, which is often used. And finally, there are resonant metasurfaces that use the phase associated with a resonant optical response. And I want to go a bit deeper into that, because that's the type of metasurfaces we are mainly working with. And when looking into these resonant metasurfaces, again, there are different kind of resonances you can utilize. So the maybe simplest type you can have are Mie resonances. Yeah. So the whole field mainly started a bit from plasmonics, yeah, where you have these plasmonic resonances in the structures. But okay, plasmonics is good for many things, but it's also usually very lossy. Yeah, so one big advantage if you really want to move towards, or think about high efficiency devices is to use to all dielectric platforms. And interestingly, if you make small, pieces of low-loss, high-index material, you can also support local modes in them, which can basically be described by Mie theory. And I show here the 2 lowest order modes that you can get in there. If you have such a high-index dielectric sphere, you get, for instance, an electric dipole mode and a magnetic dipole mode, the latter being characterized by such a circular displacement current in there. And they radiate like an electric dipole or like a magnetic dipole, as you can imagine. I will come back to that. And surely there's also a whole series of higher order modes than in these structures, according to Mie theory, quadrupole, octupole, and so on. Yeah, then Mie resonances are quite handy. We will see them also in my talk quite a lot. But they usually have fairly low Q values, so quality factors of these resonances. So if you want to go higher, there are certain concepts that you can use. One is that of fernoresonances. Where you basically have also a high Q resonant that coupled sort of with a background or a lower Q resonance to radiate to the environment. A related concept is that of quasi-bound states in the continuum, where also you have modes that are usually dark and have, in theory, infinite Q factor, but then by introducing some artificial small tailored asymmetry, you can basically open a channel where this metasurface can couple to the far field, and by deciding on the strength of this asymmetry, you can basically tailor then the Q factor of that structure, and it can be fairly high, also in fabricated structures, reaching several thousands. And another bit more exotic concept are these anapole resonances, where one basically plays with cancellation of the far field in order to get also higher Q modes, even in single particles. So I will now concentrate mainly on the Mie resonances at first and show you a bit of our workhorse type of metasurface before really coming to the active architectures a little later. Okay, so our workhorse are mainly, or what we really started with, were silicon nanodisk arrays. So why disks? Okay, being experimentalist, the sphere geometry is a little hard to access. It's just not so easy to make. So we resorted sort of to the best thing we can do in a geometry where we do lithography and etching, which becomes sort of a disk. Yeah, and if this was actually a structure I made back in 2012 or so, my first dielectric metasurface back in the time. This is just a scanning electron micrograph of that. And if you look at the spectra of these transmittance over wavelengths, you basically see such pronounced minima, which correspond to the Mie modes in this structure. In numerics, you can then also look at the near fields and simula, as I showed you, the lowest order modes for the sphere. Also for this disk type geometry, you can then get, for these lowest order modes, you get sort of a magnetic dipole mode and an electric dipole mode, what you can identify from the near fields. Do a multiple analysis if you want. Yeah, so the first thing we did then back in the time was sort of to say, like, okay, now for the disk, for the sphere, we just had the radius, but for the disk, we can now play with also the aspect ratio of that disk. And we basically started varying the disk diameter at the constant height of this disk. And this is experimental reflectance and transmittance data. The values are color-coded. Here is the disk diameter at constant height and the wavelengths. And then what we saw, so here we had these two resonances, electric and magnetic, basically from the previous slide, the same data. And as we reduce now the diameter, these modes move closer together. They move into spectral overlap and start separating again. Yeah? So we can tune them with respect to each other now, which for a sphere, they are always sort of apart. Yeah. And then the main interesting thing that was happening here is if you look in this region here, the structure was actually getting less reflectant and more transparent. Yeah? And this was not a bad sample or something, but we really could find that this is quite an interesting effect where this electric and magnetic dipole mode are overlapping. And in numerics, we can basically, even at that time, we could cultivate that and show that in this regime of overlapping electric and magnetic dipole, we could get this very high high transmittance of the structure, while the phase was undergoing a 0 to 2 pi phase variation. For single resonance, you always only get a pi phase variation, yeah? And we could also look at it analytically, basically modeling each disk as a, or this area of disks as coupled electric and magnetic dipoles. And in this ideal model, one could basically get such a dead flat T-equal unity line and this phase of 2 pi variation basically reproduced. So what's happening there? And so this is the simple qualitative explanation, which basically just shows the emission profiles of the electric and the magnetic dipole. And while they both emit like such a donut pattern, you see that the light propagating in opposite directions for the electric dipole, the electric fields are parallel and the magnetic fields are anti-parallel, whereas this is the opposite for the magnetic dipole. So if you superimpose the two in phase, you will basically get constructive interference, in this case here in this direction, and destructive interference in the other direction. So it's a directional scattering effect. It's called a Huygens source, such overlapped dipoles. And now we have basically an array of them. It's a bit more complex because we also have an incoming field exciting these dipoles, but one can write that down and really find that such a structure becomes really transparent, but the strong resonant response of the structure is still there and shows in the phase. Yeah, and if you think about wanting to manipulate the phase as a function of in-plane position in your structure, that's of course very useful because usually we want to have high transmittance of our device, right? And we need 2 pi phase coverage to really make any kind of phase mask we want to achieve. So that seemed very useful for that, and indeed we spend a little bit of time then to show some proof of principles. The very first thing was this simple Gaussian to vortex beam shaper. We moved on to show a simple hologram, probably not the best hologram in the world, but enough for us to show that this really works. And maybe the most recent of this pure wavefront shaping we did was basically some three-dimensional imaging. This was together with Frank Setzfand's group, and the metasurface was a phase mark creating such a helical point spread function. And then if you image a scene through that and apply some image processing, you can basically derive depth information and get a depth image of your scene. So these are just some examples of this pure wavefront shaping that you can do with these type of metasurfaces that are basing their functionality of the overlapping electric and magnetic dipolar mirror resonances. And we call these metasurfaces Huygens metasurfaces because they are composed of these Huygens scatterers or Huygens sources. All right. As I mentioned before, of course, this is not the only way how you can manipulate the phase of a light wave as a function of in-plane position. However, we are really still very interested in these resonant metasurfaces, and I hope on this slide I can convince you why it's really worth looking at these resonant systems. So the one thing is, if you have a resonant system, it comes with strong spatial and spectral dispersion immediately. And this means such a metasurface gives us the opportunity to tailor the frequency and angular sensitive optical response. If you think of wavefront shaping, for instance, you can make a lens that only has the lensing profile for a particular wavelength, but not for another. Or you could stack these lenses and make basically focus different frequencies at different points, for instance. Actually, we're doing this right now also as a little bit of a side project. Then, if we have a strong spectral dispersion, it also means that we can more easily tune or switch things. I will have another slide on that showing it. And then the other big dimension of these resonant systems is you can now see this metasurface really as an array of resonant nanoantennas. And each little nanoantenna enhances the electromagnetic near fields. So the metasurface is capable also of enhancing and tailoring light-matter interactions. And as you will see in the talk, we use this, for instance, for enhancing and tailoring nonlinear optical effects, emission phenomena. But I put the 3 dots there because if there's your favorite light-matter interaction effect, I'm happy to talk about that. All right. And this brings really us to the concept of active metasurfaces, so going away from this pure passive wavefront shaping functionality towards active systems. And active is used in different ways in the literature. So some people say active is active tuning or dynamic tuning. Some people say from the semiconductor community, usually thinking of an active semiconductor, meaning an efficiently light-emitting semiconductor. And we're just using this term now for everything that's not passive. Yeah? So basically tunable light emitting. We also capture nonlinear under this because this can also emit light and do interesting stuff. Yeah? All right. So if we go to this field of active metasurface, and again, maybe one wants to think about what application perspectives this would have, this opens, of course, a whole bunch of new possibilities. Yeah. So if you think of tunability, instead of just making passive optical components, one could have adaptive optics, light modulators, and so on. I always show, again, one of my favorite works from literature here. This is from Arseny Kuznetsov's work here, where they made such a dynamic beam deflector. Light emitting, of course, if we emit light, we can immediately think of lasers, displays, light sources, yeah? And yeah, here's again, it's again Arseny's work, actually. I think this laser, no? Yeah. Then for nonlinear, we're accessing really the realm of, on one hand, these ultra-fast all-optical effects, and also coherent and quantum light sources. Yeah, so I think it's really worthwhile to look at these active systems and particularly at the resonance systems that help to enhance or to really enable these functionalities. Okay, so now my plan for today was to go through these 3 points basically and show you just a bunch of activities we do in each of these pillars, if you want. And the first thing I have on my list are the tunable ones. So again, I have a little cartoon in the beginning. So I guess you may have guessed this already. So this is again our metasurface. Now the idea is we have a switch here somehow. So we have a metasurface now whose properties of functionality are controlled by external parameters, which could be, for instance, applied voltage, but also temperature, mechanical strain, some stimulus that we can, in a controlled way from outside, apply to the metasurface. So I mentioned that the resonant response and the strong spectral dispersion helps us, and probably it's sort of clear, but somehow I left this more educational slide in here. I hope you don't mind it. I will go through it quickly. Of course, if you have something like this, some optical response function that only depends weakly on your wavelengths, yeah, then if I manage to, by some change in the system, shift my dispersion here a little bit, this will lead to only a small change actually in the response. But if I have something more strongly dispersed, if I shift it by exactly the same amount, then of course my contrast that I get for the switching is much higher. So that's why resonant systems are beneficial here. So tunable dielectric metasurfaces have been quite a topic in metasurface research for a while now, and people have looked at the range of different stimuli and methods that can be applied to really getting an active tuning of the functionality. So one very simple one you can think about is mechanical tuning, basically embedding these little nanoresonators, me-resonators here in some soft matrix like PDMS and stretching that. Yeah, then quite popular topic are also phase change materials, like making resonators or somehow coupling them to a phase change material that undergoes a amorphous to crystalline transition, thereby changing the optical properties. Or also all ultra-fast, all optical tuning. This was actually something we were doing together with the Moscow guys. And in this case, mainly injecting carriers all optically in such gallium arsenide nanoresonators. I will not talk so much more about this today, but will show you our status of activities in the area of using liquid crystals for tuning metasurface properties. And we actually were also glad to be first to be able to actually tune such a dielectric me-resonant metasurface using liquid crystals with a very simple mechanism. And that was just embedding this metasurface into a nematic liquid crystal, which at room temperature is in its nematic phase, has a anisotropic refractive index tensor. Then if you just heat up the system, it transitions in its isotropic phase. These resonators here, they feel the change in the dielectric environment and respond with a frequency shift. And yeah, this is what you see here. This is basically the transmission spectrum of the metasurface as a function now of temperature. You see there is some sort of a weak change as we increase the temperature, and then there is this jump, and this is really the phase transition point. And we see we get quite a strong change and contrast in the metasurface transmittance there. Okay, you can argue that temperature is maybe not the most handy that you want in devices. So the next thing we did was voltage tuning. So again, the setup is quite similar. We start with the situation again where these liquid crystal molecules are oriented in the plane of the metasurface in one of the lattice directions. Yeah? How do we determine this? So traditionally, this is made by having an alignment layer, which is basically a brushed polymer here at the upper window of the cell. This is just mechanically brushed, and then the liquid crystal molecules orient in that direction of the brushing. Yeah? And then as you apply a voltage, because the liquid crystal molecules are little dipoles, they like to stand up in the electric field, the anisotropic refractive index tensor rotates, and again, the nanoresonators feel this change in the dielectric environment, and you see that again the spectrum here, transmittance for 0 and 70 volts, is very strongly changing. Yeah? Okay. So we had a little bit of a problem with these brushing layers, I can tell you. So it was not super homogeneous, for instance. Yeah. So something that and also, we can only really do it on the upper window of the cell, because if you would apply such a layer to the metasurface, I mean, if you brush it, you would destroy your metasurface. Yeah. So we wanted to have that a bit more controlled, and you can see this here. So this would basically be the situation where only on the upper window of a cell we have an alignment layer, and then we look at this. So this is the metasurface, the black one. We have this in between two polarizers and just light it up from the back. So everything that is black basically shows you alignment errors and defects in this structure. So what we really want is something homogeneous, and so what we were able to do with some collaborators from Belarus, they provided us with a photo alignment material that we could coat both on the upper window of the cell and on the metasurface. And because this is a photo alignment material, instead of mechanically brushing, we were just exposing that with polarized light. And this we could also do on the metasurface. And as you see from these images here, it makes a huge difference in the homogeneity of this alignment area. And we used this then to show some functionalities on a rather large scale. This is 2 millimeter. We look here through a metasurface with 670 nanometer light. The light is polarized in the direction of the liquid crystal alignment direction at the beginning. And then we had some structured electrodes where we started applying a voltage. And you see that this way we could now shift the resonances in a way that the structure was getting less transparent here. Okay. I should say this is probably not the most impressive display you have ever seen, but there are some interesting things about it, and actually some companies got interested in that, because the interesting thing is that here the switching does not happen really, it's not necessary that it happens in the whole bulk of the liquid crystal, as in a traditional liquid crystal cell. But it is sufficient to switch the liquid crystal really in a small environment of the nanoresonators. So this means potentially we can have much thinner cells, and if the cell is thin, that's beneficial, because the cell size determines the speed of the, the thickness of the cell determines the speed of the switching, also how small your pixels can get and how good your black levels can get. So let's see, maybe if this can be cultivated, this could be interesting for faster and higher definition liquid crystal displays. Okay, but probably this should transition to more applied research at this stage. For us, it's a bit hard to have these electronics associated with such displays. So we are looking more at, again, at new, more fundamental properties of these cells. And one thing we were interested in, I showed you now tuning with temperature, and I showed you tuning with applied voltage. So in principle, this liquid crystal gives us the possibility to have inherently a multi-responsive behavior. And that's, we were interested if we can really use this now to access also new state space in the system by combining more than one stimulus applied to the metasurface. And Chengjun here did this when he was still working as a postdoc with my group. And yeah, basically we have now both. We have both a heating plate and an applied voltage in such a cell. This is how it looks like. And yeah, then we can basically look at voltage-dependent temperature tuning or at temperature-dependent voltage tuning. And you see, indeed, the two influence each other. Okay, this is semi-interesting. Can we do something useful with it? And I think maybe the most interesting part here is that by combining the two stimuli, we can get in a regime of polarization-independent tuning. So both tuning mechanisms I showed you so far were always for the case that the light was polarized in the pre-alignment direction of the liquid crystal, because that is where you have the strongest change in the refractive index as the liquid crystal goes to isotropic phase or standing up in the field. But here we can basically compare two situations which are both isotropic basically for a normally incident light field, which is the isotropic liquid crystal case, and also the upright standing voltage at low temperature. Yeah, so the applied voltage upright standing liquid crystal at lower temperature. And this way, yeah, you can see that for both polarizations, the tuning effect is not as strong anymore, but it is fairly polarization insensitive. Yeah, and another thing was, can we also use maybe the stimuli like think of them like a logic gate, applying combinations of them? Yeah, and we're also looking at that, and only this combination, so for the resonances we had in our system, only this combination of 0 volts and room temperature was sort of creating such a highly transmittant state, whereas all other states were sort of leading to strong suppression of the signal. Now we have two stimuli, temperature, voltage. But what about light? So I told you about the photoalignment material, and that's actually exposed by blue light, blue polarized light, to predefine the alignment direction. However, we can also use it as a stimulus, right? So if we can precondition the cell, nobody keeps us from also using that on the assembled cell and basically reorienting our liquid crystals with this light by changing the photoalignment layer. Yeah, and this is actually also what we did, and to show this a bit better, we used actually a spatial light modulator to basically expose only in a certain region here in such a circle, and yeah, then we can measure the transmittance in the two areas, which are now differing by the direction of the pre-alignment of the liquid crystal. Yeah, and if you look at the delta t of these two curves, and you basically, at these two wavelengths, we can then look at the transmission, and you see sort of the bright and dark areas flip their sign. Okay, so this is, so the nice thing here is that we can also quite easily address or tune the metasurface with some spatial variation. Yeah, so with voltage, it is actually for us as a research lab quite difficult to have something like a pixelated environment with high definition also. But here with tuning with light, yeah, we can sort of easily address any kind of complex spatial distributions in there. All right, so this is what I want to show you on the liquid crystals. I will move on to a different kind of active system, but I should maybe look at the time. Okay, good. And this is, here we're moving now to responsive polymers. Again, we stay with such a multi-responsive environment. So we can do this kind of research. Oh, I actually didn't have this on my acknowledgement slide because it's more recent. So we're collaborating with the group of Felix Schacher from the chemistry department in Jena, who are able to synthesize such polymers, photoresponsive polymers. And yeah, basically what we do now is we look again at metasurfaces, but because these polymers, they can change their refractive index also as a function of light exposure, so UV exposure, or heating above a critical temperature. But the refractive index changes you get there are much smaller than for the liquid crystals, about an order of magnitude less. Yeah? So for the liquid crystals on the order of 0.2, and here's 0.002 approximately. So to really be able to get some contrast, we need to use fairly high Q metasurfaces now, so we're resorting to such slightly asymmetric double bar structures that exhibit a range of high Q modes. This is just a simulation, and these are the near fields of all these different peaks. And basically, I switched to experiment now, so we made such structures. These are two polarizations, and maybe I pick out one in this X polarization now here. And if we zoom in onto this, we can now see how this resonance can be shifted around basically by applying light, heat, or light and heat. And you see the shifts are not large, but because the resonance is sharp, we can still tune this by about the width of the resonance, getting a significant contrast in the output. Yeah, we were continuing with these kind of structures, also exploring more polymers. We had now polymers that were reacting to different wavelengths, so we could really play around now using blue light, red light, UV light to shift resonances in different positions or recover the original resonance positions. Sarah was doing this. She was with us from Australia for a bit more than a year and could really show how she could, depending on this light stimuli she was applying, she could shift all these high Q resonances in different positions and also recover them. And again, for these systems, we can also, again, use spatial light modulators to do this kind of switching only in particular positions with some random pattern that we project the switching light onto the metasurface. Yeah, and this is my last slide for tuning. Maybe so far these liquid crystals is known from displays, so they are sort of several milliseconds response times. Also the polymers are much slower, so if we just shine the light on them, usually we have to wait for a couple of minutes to really see the effects. So what about ultra-fast, complex wavefront control? And here I just want to share a recent work with you that we published this year. Artyom, postdoc in my team, until recently was the main person in that, where we combined a WSC2 monolayer, so a 2D material, with a strong second-order nonlinear response with a silicon nanostructure. So we did complex wavefront control for the second harmonic light, and the way it works is basically we perform pump-probe experiment, if you want, and depending if the pulses arrive simultaneously or after each other, this 2D material produces the second harmonic in two different polarization channels, and then we can use a polarization-dependent metasurface to transfer this polarization state into a complex wavefront. And what we showed was basically three types of switching: the diffraction switching, Gaussian to vortex beam switching, and also topological charge switching in these structures. And I think I haven't seen any work that could switch vortices so fast before. Okay, that was the switching part. I will now go on to the light emitting part, so the second pillar in the active functionalities. There's again such a cartoon, and now the main idea is basically for a light emitting metasurface, we want to get rid of this input light field and have the metasurface by itself emit the complex light field. So for this, it's a useful model, I think, to consider the metasurface an array of resonant dielectric nanoantennas driven by some localized sources, because what we typically have to do now to put any kind of light emitters, nanoscale light emitters, and integrate them somehow in the metasurface architecture. Yeah, what can we expect the metasurface to do? Okay, it's in particular, if we have higher Q modes, you can see this like a cavity. Of course, the Q factors are far from what you get in your microcavities here, yeah, so orders of magnitude less. So in experiment, we get a couple of hundreds typically, up to, yeah, or mean resonance, maybe a few tens, yeah. But we can expect a certain brightness enhancement through different factors like excitation enhancement, potentially quantum yield enhancement, in particular if the emitter was rather bad in the first place, yeah. Extraction efficiency enhancement, or also collection efficiency enhancement by shaping the emitted pattern. And then coming or staying a bit with this last part, I think particularly for shaping emission patterns, the metasurfaces are quite useful because we have many degrees of freedom now to tailor what is being emitted. On the one hand, we can engineer the individual meta-atoms, each of them acting like a little antenna, and also the effect of the array or arrangement. So basically, if you think in terms of scattering problem, you could say you can tailor both the form factor and the structure or array factor of your structure to get some desired output. Okay, here's a little bit of how we started and also others started in the field. Back in 2015, we just did a simple experiment putting some quantum dots on top of a metasurface where we could see the shaping of the spectra. We also looked at emission from basically fluorescent glass and how we could shape that emission with the metasurface. Others were also using, so this is work from a group in China who were putting germanium quantum dots into a silicon metasurface and could see significant enhancement of the emission. And also, I shouldn't forget this lasing work, which I showed before by Arseni's group in Singapore. Yeah. So these are some examples and what has been happening in this realm. And now I want to show you what we've been busy with in the last couple of years, and this is a bit of a particular emitter system that we're interested in coupling, which are magnetic dipole emitters. So the nice thing is sort of in the metasurface, if you think you have these me modes and you have both the electric and the magnetic multipolar modes. So somehow it seems a very intuitive idea to not study also the common electric dipolar emitters, but also to see if we can somehow selectively enhance magnetic dipole transitions in materials. And we started quite easy, again, with just such a me-resonant metasurface, which was a silicon metasurface, and we coupled that to the emission from europium 3+ ions. And here's the term scale of the europium. So this has one transition here, drawn in here, which is dominated by the magnetic dipole. And you may already see from the spectrum, which is here, so this little bump here would be the magnetic dipole transition, and normally the system is still dominated by the electric dipole transition, which is at slightly larger wavelengths. Yeah, and this is around 600 nanometer wavelengths, so silicon is already absorbing there, but this was sort of the system we had at hand there. And even in these fairly bad resonances, I must say, because the silicon really absorbs, it's really difficult to tailor very particularly the modes. We could already see that this branching ratio between electric and magnetic emission in the europium could be modified by putting the material within a polymeric matrix onto this metasurface. Okay, this is sort of summed up here. So, and I say like the problem really was silicon is absorbed around 600 nanometer, which is why there is now not a huge effect, but one has to really look at the data to see it. So now we moved to more recently we moved to such a design using titanium dioxide as the material of our metasurface, which is highly transparent in the visible range, while still providing sufficiently high refractive index to see these zoos of modes that we're interested in, like me-resonances, or in our case here, actually such a Fano-resonance, or if you want, quasi-bound state in the continuum resonance, so much higher Q factor now than a simple me mode. And we did a similar thing, so this metasurface was made, this is how it looks like, doesn't look particularly beautiful, but actually has nice spectra, and then again we put the europium 3+ in a PMA matrix on top, and first thing we can see, if we sort of map the fluorescence signal as a function of position, we could see both for the magnetic transition at 590 nanometer and also for the electric transition at 610 nanometer, the metasurface was enhancing the signal, but from the image you already see that it's enhancing more strongly for the magnetic transition. So basically, if we look at the emission spectrum now, for the you remember maybe this reference spectrum where this magnetic dipole emission was only this little peak, you can't like little bump there, and the electric was here. Now we see that actually in the signal that we collect at the detector, the magnetic transition becomes the dominant channel here. However, just from looking at the spectra, it's sort of a bit difficult to tell now what the dominant mechanism is in this enhancement. And therefore, we also looked at the backfocal plane of emission for that. So Ayeshi was mainly working on that. So here you see the experimental images at the magnetic and the electric dipole transition frequency. And backfocal plane, I think you're quite, you use this yourself a lot. So basically each point in this image here corresponds to a direction of emission. And the center is just emission out of the plane. And you see they differ a lot for these two, particularly for the magnetic dipole. We are really at the condition where the metasurface directs light sort of normally out of the substrate plane, whereas there is a minimum at the center for the electric transition. And we can also calculate that using the reciprocity principle in these structures. And it looks quite similar, I would say. And now you can imagine if you collect the signal now with a relatively low NA, then of course you're sort of efficiently routing the two different channels into different patterns, and you can have different collection efficiencies for them. Yeah, something that is not published yet but sort of happening is that we are interested now in looking at more effects where electric and magnetic dipole emission shows us different effects of coupling to the nanostructures. Yeah. Also, what I showed on the previous slide, this is mainly a wavelength effect, but you can also think of nanophotonic architectures that couple by themselves more efficiently just to the different nature of transition. Yeah. So, for instance, if you compare sort of electric and magnetic Purcell effect, which would be favored by different near-field patterns, and the problem a bit in seeing this in experiments so far was to, that we really had these emitters always everywhere, and if you have a small effect and then you have them everywhere, yeah, it's sort of buried in the noise if you want, yeah. So Marijn here now is working on making like defining where we put these electric and magnetic emitters, basically mixing the europium 3+ into an e-beam resist and exposing that. And you see, yeah, so he's making some progress in making some images and also some little dots, and also in using sort of two-step lithography, for instance, to put this kind of material in the gap of such a dimer. Yeah, and we hope that this way we will be able to look also at some interesting effects to really look at the very precise coupling in a particular near-field position. Let me check the time again. Oh yeah, I should speed up a bit. So I show, this is really ongoing work, maybe I show it only very briefly. So we also started to look at some lasing in such titanium dioxide nanostructures, basically putting laser dye in a polymer coating again on top. And yeah, maybe I don't go into details here. So this shows also lasing behavior. And you see also backfocal plane images again below and above threshold. So we can sort of get an out-of-plane lasing from this dye at 568 nanometer wavelength. Okay, I was speeding up a bit because I don't want to skip completely the nonlinear and quantum part. So I do have a reminder on nonlinear optics, but after spending the day here, I think I can safely pass this on, yeah. So and leave it. So it's just reminding of the polarization for a lossless dispersionless medium with instantaneous reaction, and sort of explaining the Chi2, Chi3. But I realize, you know, and the nonlinear optical effects arising from that. But I think in German you say you bring owls to Athens, yeah. So I think I can safely skip that. But maybe motivate a bit now how we want to use the metasurface for nonlinear optics. And of course, with Maria's team, she's also working in very similar directions. So some things may seem familiar now. Yeah. So so what kind of effects are we interested in? So again, I have this little cartoon. So now here's our metasurface again. We would come in with light of some frequency omega, and so far we looked at the same omega on the other side, and now we want to look at the generation of new frequencies like second or third harmonic. Why is this interesting? Okay, let's say we have again a resonant metasurface, so we can have some near-field enhancement, which helps to enhance the nonlinearities. The materials we use typically can have very high intrinsic nonlinear susceptibilities, yeah. and also fairly high damage thresholds, because as compared to plasmonics, we're not strongly absorbing at the fundamental frequency if we design our system correctly. But maybe the killer argument here really is the last one. The structures have sub-wavelength thickness, so while yeah, if you work in nonlinear optics, usually phase matching is really one of the things you spend a lot of time and thought on. And for these sub-wavelength thickness structures, yeah, basically no phase matching is necessary anymore. So this opens up a whole new universe of nonlinear optics, if you want. So these harmonic generation is interesting, but of course we can also go a bit more complex, do some frequency generation, which is, or also turn around this process if you want, and look at spontaneous parametric down conversion, where a pump photon spontaneously decays into two lower energy photons. And I think it's particularly interesting, and this is also what Maria works on a lot. To look at, to use such metasurfaces then as entangled photon sources based on spontaneous parametric down conversion. And yeah, it's quite obvious, single and entangled photons are of course a very important resource in quantum optics, quantum imaging, quantum sensing. Yeah, while the spatial degrees of freedom that are offered by the natural nonlinear crystals are very limited. So here we really get the handle on this and can start tailoring things and see what other yeah, fields we can generate there. Okay, so when starting, so I will concentrate now on the Chi2 processes in these materials. The very first thing we did was actually third harmonic generation in a silicon metasurfaces, together again with the Moscow guys back in the time. Yeah, but soon after we started working on the second harmonic generation, and not only us, also, for instance, the Italian guys and Giuseppe Leo and Costa De Angelis were also looking at gallium arsenide or AlGaAs nanocylinders. We were working with Igal Brenner, who many of you here also know, to do this in a metasurface. So everyone for second harmonic was sort of concentrating on these 3-5 semiconductors like AlGaAs and gallium arsenide. Now these materials are a bit tricky. They are not traditionally used in nonlinear optics a lot, because basically if you would just put a 100 oriented gallium arsenide wafer and try to look for the second harmonic, this would be dark. Yeah. One thing is the nonlinear tensor is quite complex. It mixes all the field components. So if you come, yeah, so basically no second harmonic would be generated such that it can propagate along the optical axis in this crystal orientation. And even if you somehow try to play with that, typically the second harmonic would be strongly absorbed then, yeah, if you pump in the near infrared, because yeah, the band gap is not very large in these structures. So if you come to this nonlinear tensor, this shows very nicely in experiments this problem that you're not emitting along the optical axis. So this is work by the group like Dragomir Neshev's group. This was work by us in Jena. This was for a single cylinder of gallium arsenide. This was for a metasurface, and you always see in the back focal plane, yeah, there's sort of a minimum here at the center, so no second harmonic light emitted in this direction. So what can we do about it? One thing is we can rotate the tensor, and so this is not the first work that showed this. This was also done in gallium arsenide by us and also others. Was a big thing, but so we're now looking also at gallium phosphide to do that. And gallium phosphide is nice because it has quite a large band gap, so it's transparent over large ranges of the visible. Plus, it's still a 3-5 semiconductor. It still has a zinc-blended type lattice structure and a strong second harmonic. Yeah, and we can also use now a crystal orientation of 110, where this emission along the optical axis is not suppressed. And Muyi has developed all the recipes for structuring that, and basically was able to get mirror resonances and to measure second harmonic generation from this, immediately getting on par with the efficiencies that in very much more highly engineered systems of other materials were shown just in such simple mirror resonators. And if you look at the back focal plane, we also see that there's not a minimum now at the center, but a significant fraction of the light is really emitted along the optical axis. The other thing one can do is to go to a completely different kind of material, which doesn't have this problem of mixing of the field components. And lithium niobate is very nice here. It has a very high transparency range, really from UV to mid-IR. And it's a bit hard to nanostructure, but in the Jena clean room, they can do this quite nicely. They have developed this over many years. And one gets some metasurface looking like this, or also some others by now. And so maybe some of you have met Anna. She spent some time here with Maria also. And but the first thing she did was basically looking at second harmonic generation from a lithium niobate metasurface. So lithium niobate has a nonlinear susceptibility tensor, like second order, that is dominated by just one element. So it's much more well behaved than for the 3-5 semiconductors. And she was comparing sort of off-resonant cases and different mirror resonances, and could basically see some enhancement if she was looking at the resonant excitation of these structures in the second harmonic signal as compared to the off-resonant case. And again, in the back focal plane, you see a nice spot in the center, so no problem there. So this I already said. So now I will briefly show this work, which you have probably seen presented by Maria and her posters. So this was really joint work measured here. So the same metasurface you saw here, where we first looked just at second harmonic, was brought by Anna here to the MPL, and in Maria's lab, photon pair generation via spontaneous parametric down conversion was measured, and indeed, by the enhancement through the resonances, an enhancement of more than 2 orders of magnitude of the biphoton rate could be detected in there. Okay, so now I already come to the outlook. So if we look at the road ahead, I mean, something that's probably quite clear and obvious is that now we have these 3 things of tuning, light emission, nonlinearity. But there's so much more room to bring these things together, like to have, for instance, dynamic, light-emitting, and nonlinear functionalities with spatial control. Also, if you think of applications like ultrafast wavefront shaping, smart light sources, on-demand sources of tailored quantum states, and so on. So there's a lot that can be done, and also, of course, a lot of new material systems that can be explored to establish such effects, such active effects in such platforms. And the other outline slide I have, is this one here. So something we start getting quite interested in. We were briefly talking about this with Professor Marquardt before already. So we think that our active metasurface could become quite interesting building blocks for diffractive neural networks or diffractive deep neural networks. Basically making a implementation of neuromorphic computing, if you want, using metasurfaces. And this is being done in the literature. Like people use diffractive optical elements to stack them in these ways and perform, for instance, different classification tasks. That works already quite well. But we think now that having active metasurfaces, which could introduce some nonlinearities to the system, some reconfigurability or even tunability, could be quite interesting to get the true depths of such systems. To sort of, if you want to implement this in the optical range, it's also very difficult to align. So if we can maybe use these polymers to locally change a little bit the environment and really correct for errors in the system, or even with such tunable systems have something like trainable models, or even look at quantum effects in there, we think this could be some interesting direction to look with these kind of systems. Okay, I'm at the end, so thanks a lot to the current team shown here and also the funding. Maybe one thing to highlight if talking about active metasurfaces is this graduate school. So this is a DFG-funded international research training group together with the Australian National University that we are running since almost 3 years now. So basically our graduates come to a Ph.D. jointly at ANU in Canberra in Australia and FSU in Jena. And that's been very exciting to have the people traveling forth and back and spending time at both institutions. And some of the work I showed was also done really by these students. So most importantly, thank you for your attention. I'm happy to take any questions.
Much for the fascinating talk and right on time. I'm sure there are many questions. Who wants to start?
That's good.
Wondering what is the maximum reflectivity you can get from a metasurface?
That's a good question. So we haven't tried to really tweak that to the maximum, but there are some works that really look at dielectric mirrors or magnetic mirrors also. And engineer that. It gets fairly high, but I cannot tell you the digit after the comma at the moment.
My question would be if you implement them in terms of cavities, so you make cavities with 2 metasurfaces. Is there any work in that direction? Or?
We are not active in this range. I have seen some people doing that, but I would have to search again for the names to find that. So don't have it. I mean, this first looking at these dielectric metasurface like mirrors. This was also, I think, Igal was, or no, Jason Ballantyne was doing that, I think, and really trying to optimize and quantify the reflectivities. And he found then some quite broadband regime if bringing the resonances in the right distance to each other. So people have been looking at that, but I don't remember the exact digits or. Yeah, it will probably not rival a well-grown dielectric mirror stack, but could be interesting to have this as an in-plane variation, for instance. Yeah.
Next one is Stefan.
Yeah, thanks a lot. I enjoyed your talk a lot. On your outlook, you said something about on-demand quantum state generation or something like this. This caught my attention. How do you want to do this with that? Surfaces?
Yeah, I mean, we do have ingredients for that. We have metasurfaces that can generate entangled photon pairs. We do have methods to tune a system. Yeah. Of course, there will be challenges in putting the two things together, but I think this will be an interesting thing to look at. For instance, embedding now such a Chi2 metasurface into a liquid crystal or into such a tunable polymer, and see if we can switch, if we can shift the resonances around, which in turn will influence then the like, let's say at the given frequency, the biphoton rate.
So I was more interested in the on-demand. So
on-demand. Oh, okay, maybe.
Things, maybe.
Okay.
Or did you think of implementing some single emitters somewhere, or whatever is not, or is truly on-demand?
No, I was more looking on demand, not in this classic. Maybe I should change this word, to be honest. Yeah. So I think in the quantum optics community, this is something very well defined, and which I maybe not use in the completely proper way right here now. So I was more looking at tailoring the properties of the emitted biphotons, for instance, by changing resonances in the structure. So or like tailoring dynamically adjusting the properties. Maybe this would be more the better way to pose that.
Thanks.
Earlier in your talk, you showed that the situation that the scattering of the magnetic transition dipole and the electric one, they interfere destructively in one direction. Have you realized that? Because later on, in your system, you have different resonance for the electric transition dipole, and I think you need overlap for that to happen. So.
Yeah. No, it's one of our workhorse platforms. So we have realized that many times, starting just from a homogeneous metasurface to map out what is the transmission. We have measured the phase and everything. Yeah, just mapping this homogeneous system. And then once this was established, we have moved on to these. I showed a few examples of wavefront shaping. Yeah, like you remember, maybe there was this. Which slide was this? Maybe 10 or so? Let's see. Yeah. So these were all these Huygens metasurfaces. So these were all operated in this regime of overlapping electric and magnetic dipole, and basically showing high transmission this way. And by changing a bit locally, mostly the lattice constant. Then in later works, we started also changing a bit the diameters and so on. We could then tune both resonances a little bit. but simultaneously, so that we keep this overlap regime of high transmittance while changing the phase curve. And then if you look at a particular operational frequency, we're sort of cutting this phase curve at different positions. And then, for instance, in this very simple example, in these 4 different quadrants here, different phase values are then established. So
partial overlap between the 2 resonances.
No, the resonances are engineered in a way that they have very similar Q factors and also almost identical resonance frequency. Yeah. So they are really overlapping in a fairly broad band range. Yeah. So that in all positions, these 2 scatterings sort of play together to show the high transmittance.
How about the magnitude of the scattering? Because for perfect distractive interference, you need to balance that as well.
Yeah, that's right. Yeah, this is you have to engineer that by mainly the environment also of these. If you stick yourself to silicon resonators, yeah, what you do is you have to adjust the aspect ratio in the first place to get this kind of overlap. But then the strength is indeed, also the Q factors of the resonance are still a bit different. What you can do then is to play with the environment, like basically change the refractive index of the embedding medium, and that brings the strength and the width of these resonances closer together. And you can also play a bit with the distance between these. So you have all these engineering degrees of freedom. You just optimize everything, and then you get quite close to a situation where the resonance curves are almost overlapping, and you really get a broadband. I mean, you can see it's like a broadband Kircher effect, if you have heard about the Kircher effect. Yeah.
First, Masha. Yeah.
Thank you very much for the talk. I wonder, when you spoke about this orienting liquid crystal molecules with light, so what should I know about this light? Intensity, frequency, can it be anything, or?
Yeah, sure. We use blue light. Yeah, the exact wavelengths I would have to look up, but it's blue. But it's polarized, and it's just an LED array.
Has it to be resonant somehow?
No, it's not really resonant. You can use some range. It need to have sufficient energy, and probably how wide is this range? I cannot really tell, but so this blue range it doesn't have to be super precise, yeah. So just buy blue LEDs and it will work. And I think you can also detune a bit and it still works.
Talking about the orientation of your liquid crystals, before you see the brush to orient your liquid crystals, what is the physical mechanism behind? Do you induce some scratches or deposit charges or material?
Yeah, that's a good question. We were also asking ourselves that. Masha is already smiling. So people tried to study that. And actually what I remember is that they, for instance, made artificial scratches lithographically, for instance, but they did not show the same behavior. So there is probably interplay of several effects. Some of it is just the change in the topography due to scratching, but more of it is probably that in these polymers you also sort of, by the constant brushing, you sort of align these molecules, but it's actually not super well understood as far as I know. Yeah, so people try to maybe Masha can jump in if she knows more about that. But it's a tricky question. So I think it's not 100% understood, and people try to look, but it's not just a topography effect. There is also something happening in the material.
Hey, do I see any more questions? Masha.
One more question. I was always wondering, and sorry for being ignorant, you show separately Fano resonance and quasi-BIC. Or is it different? And if it's different, then why?
Okay, probably it may depend on the person you ask here what your answer will be. Okay, as I see it, it's... Okay, let's see, maybe the cubic or the bound state and continuous, maybe the more general concept if you want, yeah, to have something. I mean, you could maybe at least I would say you have something like a dark mode, and by breaking some, which of course if it's dark and there's no absorption, in theory you can sort of get infinite Q factor, yeah? And then you introduce some imperfection, like some symmetry break that you can do in a very tailored way, and this way a dark mode becomes a little bit bright and couples to the environment. And often what you see for these kind of modes is a Fano resonance in your spectrum, actually, because Fano resonance, comes from a different kind of notion, mainly from atomic physics, right, where one saw these asymmetric line shapes, and they could be explained by the interplay of a narrow mode that interferes with some broad background, and this way you don't see sort of this Lorentzian line shape, but you see sort of this asymmetric line shape, depending on your coupling and so on and so forth. So I would say in nanophotonics, it's a bit in some cases you could call it both, whatever you prefer maybe. But often we see Fano resonances, but follow these design principles of cubic, so quasi-bonds in continuum. But I don't know. Maybe in the end it doesn't matter so much. What matters, I think, is you have a dark state and you break some symmetry to couple this in a very tailored small amount to the far field. Yeah, that's how I see it.
Good, thank you. Do I see any last question? Doesn't seem to be the
Hello?
online questions.
Hello. Hello, Isabelle. Very interesting talk. My question is about the active tuning of the of the resonances, actually. When you tune the resonances with liquid crystal, especially, like from what you've shown, like the ED and the MD, both the resonances are getting tuned. But sometimes, what I find is that these resonance positions, they actually switch. Meaning, in optical metamaterial, the first resonance peak should be the MD, right? I mean, the lowest wavelength peak would be the MD, and then the ED, then MQ, EQ, like that, right? So sometimes the position of MD and ED seems to be switched. What do you think?
Okay, that's right. Yeah, so in the sphere, it's very clear what your your lowest order mode will be the magnetic dipole resonance, according to me theory. Yeah, but as you also saw from these very first experiments we did in the disk, doesn't have to be a disk. You can also sort of squash your sphere to have some kind of rotational ellipsoidal there. Yeah, in this way you can tune the modes in a way that they can also switch their order. Yeah, that's possible. So if we have this rather low aspect ratio, we observed the electric dipole mode to be the lowest order system, and then as we sort of increase the aspect ratio, you saw them switching and crossing, and it goes back sort of to the situation like if you have an aspect ratio on the order of 1, we're back to this, let's say, sphere order or me order. Yeah, so but this is something you can engineer by the design, and of course it can also depend on the environment. So it's actually for the liquid crystal quite interesting, because in this anisotropic environment, it's actually a problem. Yeah, maybe you have noted that I have not shown you any tunable wavefront shaping, because
I've seen some papers on that. Yeah, I mean
this
like
is really hard to get.
I've been following.
Yeah, you will be tuning sort of in different directions, and so it depends also on the environment. What is the lowest order mode? Yeah.
Very good.
Okay, so if it's a spherical particle, we won't be able to, tune the ED versus MD position probably, no? So it depends on the aspect ratio.
For a spherical particle, just in a homogeneous environment, no, me theory will give you that order. Maybe I could think if you have an anisotropic environment, I'm not sure. Maybe you can change it, but I haven't tried that. But there's a chance, at least, to change the mode distance. Yeah.
Okay. Thank you.
Okay, so while we're at it, maybe we can also take the question by David Ortega. Can you unmute yourself if you like?
Yeah, excuse me, on the slide where you indicated that you can put a light source at the entrance that crossed the wavelength by tuning.
Maybe too difficult, but we can try to figure this out later.
Not 100% sure what is meant. The slide where...
Okay, maybe we jump to the next question. Can you develop a new kind of antenna? Probably this is something that makes sense.
Okay, a new kind of antenna. You mean by these meta-atoms? I mean, actually, these building blocks of the metasurface are meta-atoms. As I said, you can think of them also like little antennas. And one thing that works quite well, at least we never showed that in experiment, but we had a lot of numerical work going on. Just using such a nanocylinder and coupling a dipole to it, you can get a fairly directional behavior that you can also tailor. So I would say yes. Yeah, and at what frequency would it work? Yeah, okay, this depends on material and size. So these are geometric resonances. You can tune the sizes, and this way you can adjust the frequency. So typically we work in the near infrared with silicon, and for visible we use, for instance, titanium dioxide. So this would be the typical frequency ranges for us to work, but it's not limited to that. Yeah, so if you want to go larger, you can go to mid-IR, or if you find a way to make very small antennas, you could also push towards UV maybe with some right materials. Yeah.
Okay, very good. So maybe in view of the time, we stop at this point, and then we just try to quickly answer the remaining questions online by typing. And so let's join me, please, in thanking Isabelle again.